Good morning. Good morning. Good morning. Salutations. Waiting for about one more minute. All right, I'm going to get started. Greetings, everyone. Today, we are going to talk about something called angular momentum. Okay? Angular momentum. All right? And angular momentum is denoted by L. All right? And intuitively speaking, angular momentum kind of quantifies the amount of spinning. That's what angular momentum quantifies, how much spinning is happening. All right? In some sense. All right? So I'm going to start off by giving you the true definition of angular momentum, which is it is position vector cross product with momentum vector. Okay? Which could also be written as position vector, mass times position vector cross product with velocity vector. Okay? Because P equals mv. So, like that. All right, so that's the real definition of angular momentum. If you have a bunch of particles, then the total angular momentum is going to be the sum of the individual angular momenta. Okay, so that's the formula. And from this formula, we can actually get the units of angular momentum. So we can see that it's a mass times a position times a velocity. All right? So that means that the units of angular momentum are a unit of mass times a unit of position, which is meters, times the unit of velocity, which is meters per second. So angular momentum is measured in kilogram meters squared per second. All right. So those are the units of angular momentum. All right. What I want to imagine is, like, let's say, for example, a particle that is moving in some kind of a circle. Okay, so let's imagine we have sort of a 3D view of the particle. All right, and so the particle's moving around in this circle. Here is the center of the circle, and here is its position vector, so this is r, and then the velocity vector is tangent to the circle, as we learned. All right, so if you were to work out that cross product, you would find that the direction of the cross product of r cross p is going to be perpendicular to the plane of the orbit. Okay, so the angular momentum vector, if you have, for example, a planet orbiting the sun in a circular orbit, the angular momentum vector is perpendicular to that plane. All right, so that's the way the angular momentum vector works. Okay. So what I'm going to do is I'm going to go ahead and take the definition of angular momentum, and I'm going to take the derivative of it. Okay, with respect to time. So that's going to be the derivative of with respect to time of r cross p. So this is two things multiplied together. So when we take the derivative, we do the product rule. Okay, but because these are cross products, when we take the derivative, the order matters. So we have to keep r and p in the same order when we do the product rule. Okay, so taking the derivative, we get dr dt cross p plus r cross dp dt. All right. So that is how you do the product rule when you have a vector product. Okay. Same thing applies to dot product. You just do the product rule, but you got to keep them in order. All right. Now, dr dt, all right, is equal to the velocity vector. And you might recall that momentum is m times v. So we have m times v cross v for that first term. So I want you to type it into the chat if you know what v cross v is equal to. All right. And notice how we have dp dt. And according to the sneaky form of Newton's second law, dp dt is equal to the net force. Okay, so we have plus r cross net force. All right, does anyone know what is v cross v? Nope. So I'll give you a hint. So the magnitude of v cross v would be, oops, you can't even see that. the magnitude of v cross v would be the magnitude of v times the magnitude of v times the sine of the angle between two vectors that are the same. So what is the angle between two vectors that are the same? 0. Okay. What's the sine of 0? It is 0. So v cross v, any vector crossed with itself is 0. Okay. So we get 0 plus r cross f. And does anyone remember what r cross f is equal to? We just talked about it. R cross f. I will wait. Waiting. I will wait 10 more seconds. Torque, excellent. So this is the cross product definition of torque. So remember, we talked about torque as r times f perp. That's the magnitude of the torque vector, but it's actually a cross product. So this is actually the net torque vector. So the rate of change of angular momentum is equal to the torque. All right? So in particular, if there is no net torque on the system, okay, if there is no net torque on the system, lost my train of thought there. Then we have net torque equals 0. So that means that dl dt, the derivative of the angular momentum with respect to time, is 0. And if who knows what it means if you have 0 time derivative? What's another way of saying that you have 0 time derivative? We talked about this with energy and momentum. When momentum has, it's constant, but what's the physicsy way of saying that? So yeah, that it means it's a constant, so that means L initial equals L final. And sort of the more physicsy way of saying that is to say that angular momentum is conserved. Okay, so when there is no net torque on the system, the angular momentum of the system is conserved. Okay, in this class, we will. So if you take more advanced physics at the college level, then the vector nature of the angular momentum is important. But for this class, we will only need to work with the magnitude of the angular momentum. So the angular momentum isn't going to be changing directions. It's just going to be changing size. In this class, only the magnitude will be important. If you deal with angular momentum conservation as a vector, you can start to analyze things like tops. If you've ever seen a top, as it precesses, it's spinning and it precesses. The vector nature of angular momentum can explain that sort of behavior, but to understand that, you really need to be confident in your vector abilities, and I guess College Board doesn't expect you to know that much about vectors at this point. So so I'm going to call that L just without a arrow over it. And so the magnitude of the angular momentum vector is going to be m v perp times r. All right. So that is the angular momentum. If you have a rigid body, okay, so this is for a point particle. If you have a rigid body, there's an equivalent form, which is the sum of the angular momenta of all the individual parts of the rigid body. And the formula in that case is I times omega. So this is the formula for a rigid body. All right. So I will pause for a second for you to write that down. So these are actually the equations that we're going to use the most. These two equations for angular momentum. All right. So let's go ahead and apply the law of conservation of angular momentum. Let's do a little example here. One of the ways that angular momentum is often used is when we're talking about a planet orbiting a star. Okay, planet orbits star in an eccentric orbit. So, as you know, orbits are in general not circular. They're actually ovals with the sun at one of the foci of the ellipse. So let's say there's the star. Then the actual shape of a real orbit is something like this. Trying to make that as symmetrical as possible. Okay. Now the point at which the planet, so the planet is going around here. The point at which the planet is farthest from the star would be this point right here. And that point in the orbit where the planet is farthest away from the star, if you play Kerbal Space Program, you know this. It's called the Apoapsis. Apoapsis. Okay. All right. And the point at which the planet is closest to the star is called the periapsis. All right. So these are special points. If we're talking about orbits around the sun, then these are called, if this particular, this is just in general, it's called apoapsis and periapsis. But if we were talking about the sun in particular, you call it the perihelion and the aphelion, because helio means sun, okay? Perihelion and aphelion. If we were talking about a satellite orbiting the Earth, if the Earth is in the center, then it would be called the apogee for geo, right? So I'll write these down. Aphelion, apogee. And then the periapsis is called the perigee. So perihelion, perigee. So these are, they just, instead of putting apsis, they put something a little bit more descriptive. All right? It is easy to calculate angular momentum at periapsis and at apoapsis. Why is that? If you look at the r vector, so for example here at apoapsis, our r vector goes all the way out here. So here's our r vector at apoapsis. And because it's at its farthest point, the velocity is actually perpendicular to the radius vector. Okay, so why is that? It's because it's especially at the apoapsis. If we looked at a point in the orbit that is not the apoapsis or the periapsis, maybe your r vector would be like this, and then your velocity vector is tangent to the orbit. You can see that these are not perpendicular. Okay, but at apoapsis and at periapsis, those are the only two places in the orbit. So these are the only two places in the orbit where the velocity is perpendicular to the radius vector. Okay? So what that means is that when we're calculating the angular momentum, mv perp r, the velocity is already perpendicular. Okay? So we don't need to do any trigonometry to calculate the perpendicular component. We just do mvr. So that makes it really nice. Okay? So then conservation of angular momentum, if we apply conservation of angular momentum, then the angular momentum of the planet at periapsis is equal to the angular momentum of the planet at apoapsis, which means that m v at periapsis times r at periapsis is equal to m v at apoapsis times the radius at apoapsis. And you can see that the masses will cancel out because it's the same planet. Okay? So that's really nice. So basically what this equation does is if you know about the size of the orbit, so you know the periapsis distance and the apoapsis distance, you can compare the velocities at apoapsis to periapsis. And in general, what you find is as the radius goes down, the velocity goes up. So the smaller your periapsis is, the higher your periapsis speed will be. All right? So basically, the more eccentric the orbit is, I believe I talked about eccentricity, which is how oval-like your orbit is. The more oval-like your orbit is, the greater the difference between your periapsis speed and your apoapsis speed. So that's a nice, useful equation. All right. Let's talk about another example. All right. Let's suppose the core of a star can be considered a rigid body. It's not really a rigid body because it's made up out of plasma, but we can consider it to be a rigid body. So it's a sphere. The inertia of a sphere is 2/5 mr squared. So it's possible to show that using calculus, that the rotational inertia of a sphere is 2/5 mr squared. Okay. Now here's what happens in a supernova. So you have a star. Okay. And the star is spinning about its axis. All stars are spinning, at least a little bit. Okay. Don't quote me on this, but I believe the orbital period of the sun's rotation is like 17 days or something like that. I'll have to look it up afterwards. Okay, so you have this star that's rotating, and it has its core in the center that's rotating. And then it has the outer surface, which is, I don't think it's called the mantle, but you have the convection zone, you have the radiation zone. You have all these different, just like you have layers of a planet, you have layers of a star. Okay, so during a supernova, the core all of a sudden, so there are a number of different mechanisms, but one of the mechanisms has the core stops fusing, and so the star starts to collapse. So the core, because it's not fusing and producing energy anymore, it starts to shrink. So the core falls in onto itself, and the entire star falls in. Okay. So the entire star starts to fall in because the core falls in. All right. But what happens is the core transforms, and it can only be compressed so much. So the core compresses as much as it can. Okay. And then it stops getting compressed. And what happens is the outer atmosphere of the star bounces off of the core. So it goes bing like that, and it bounces off, and it creates what's called a supernova explosion. Okay. And it turns out that when the outer atmosphere of the star hits the core, it actually compresses it even further than it wanted to compress to begin with. Okay. So the core gets shrunk down a whole lot as a result of that compression. Okay. And the outer atmosphere of the star gets blasted away. So you have this outer atmosphere of the star that gets completely blasted away. And that's called the supernova explosion. Okay. All right. But if we look at it, the core got shrunk down. So its inertia went down because the mass of the core didn't change, but the size of the core did change significantly. okay? Now, if we're thinking about the core as a rigid body, if the angular momentum is constant, then as the inertia goes down, the angular velocity has to go up. So as a result, exactly right, there's a comment that it's a neutron star. That is exactly correct. Or it could be a black hole. But we're going to say that this is a neutron star. So basically what happens is that the small amount of spinning that the initial star had becomes an immense amount of spinning for the neutron star because it got compressed and its size went down. Okay, so you have basically you have I initial times omega initial equals I final times omega final. All right. Now the inertia of a star of the core is 2/5 m r squared. Okay. Equals 2/5 m r final squared omega final. All right. And the 2/5 m's cancel out, so they're not important. And basically what you get is r initial squared omega initial equals r final squared omega final. Okay, so this is kind of the master equation for this problem. All right. So this is really interesting, to me at least. So basically it explains why neutron stars are spinning really fast, because neutron stars are observed to be spinning incredibly fast, and it's because of conservation of angular momentum. They spin. Now here's the thing: you often get a neutron star that is spinning about one axis, but its north and south poles, magnetic north and south poles, are about a different axis. So basically what you have is it's like a magnet that is spinning like this. Okay? And that magnet, when you spin a magnet, it emits electromagnetic radiation. Okay? So what we see is when we look at a neutron star, we often see that it is pulsing with electromagnetic radiation. Okay? And so a rotating neutron star is what's called a pulsar. Okay? And so the reason that it's called a pulsar is every time that North Pole rotates towards the Earth, you get a burst of electromagnetic radiation. So you burst, 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 burst. And they're spinning many times per second. And so it actually took a while. So we had identified neutron stars that not all neutron stars are spinning like this. Sometimes they end up not spinning very much. And so we had observed neutron stars and we had observed pulsars, and eventually someone realized that a pulsar is a neutron star that's spinning very fast. And actually, one of the tests of general relativity, Einstein's theory of general relativity, has to do with neutron stars. Okay, it turns out that a spinning neutron star gives some of its energy to space-time. And as it gives some of that rotational energy to space-time, the neutron star slows down. So what happens is gradually a spinning neutron star will slow down its spinning because of giving its energy to space-time. All right? And so we've been able to make ultra-high precision measurements of pulsars, and we've been able to observe the period of the pulsar spinning slowing down in a rate that matches what is predicted by general relativity. So this is one of the ways that we have verified general relativity. Any more room? There is another type of problem that I wanted to talk about. I'm just going to put a sticky note on top of here. Oh my gosh. Nasty, nasty fart. Nasty fart. Bug. It is another type of problem that you can have is you can have problems where you have like two disks that are on top of each that are share the same axis, but they're not touching each other, and so the you have this disk has an angular momentum of I1 omega 1, and this one has inertia or angular momentum I2 omega 2. So the initial angular momentum is I1 omega 1 plus I2 omega 2. All right? And then maybe this disk falls on top of the other disk, like so. And when they fall on top of each other, they're going to eventually start to spin at the same rate, but their inertias are going to add up. So we have the final angular momentum is I1 plus I2, because the two disks are now acting as a single object, times omega final. So this can be used to calculate the final rotation speed of two things that are spinning that come into contact. So that's kind of a useful formula. We did talk about this type of problem last year, so I just wanted to give a refresher of that type of problem. All right. So, and by the way, this is the rotational equivalent of a completely inelastic collision, because in a completely inelastic collision, two things hit each other and then they have the same velocity afterwards. Here we have two things that are spinning at different rates that land on top of each other, and then they have the same final spin rate. All right. Okay, so that is my lesson for today, and I will